How am I ever going to understand seafloor spreading?
I know, you can ask the professor for help.
Really? Okay. Professor,
Yes, dear.
I don't understand seafloor spreading.
It's hard to understand seafloor spreading if you don't understand the basics. Seafloor spreading goes along with many geosciences, the most important being convection currents in the mantle.
What, in the where?
Convection currents in the mantle.
What's that?
Convection currents are when chunks of material in the mantle float in a circular motion. The colder, more dense material near the crust sinks and pushes the hotter, less dense material upwards and to the side.
So basically the colder material sinks down because it's cold and the hot material rises because heat rises? I feel there's more to it than that.
Yes, there is. The material rises and then cools down and experiences thermal contraction, and the process starts over. The sinking material experiences thermal expansion.
Where does this happen?
This process occurs very slowly over many years and occurs all over the asthenosphere.
I don't fully understand.
Here, I'll show you. Seafloor spreading is a very simple process to understand, even for an 8th grader, once you know how convection currents in the mantle work. Now let us incorporate this into a chart. As you can see, the magma is pushing against the plates in the convection currents. Furthermore, this magma can also make it through the plates. An example of this is magma pushing up through the mid-ocean ridge. The ridge is a divide between plates. When this magma pushes through the ridge, the water from the ocean rapidly cools it. This lava then hardens and sinks to the ocean floor, which pushes previous hardened lava outwards. Over many years, this process occurs and the ocean floor slabs are pushed outwards.
Well, how come all this magma doesn't push apart the plates?
Well, it does. It's called ridge push.
I think I've heard of that term.
Well, the magma pushed up through the ridges also pushes against the ridge wall. Keep in mind that the magma is moving very slowly and how dense the oceanic plates are. This tells you that the event occurs very slowly.
Well, that makes sense. What about slab pull? The two seem to go together.
That is what I'm getting to. Before we discuss slab pull, you must first know the difference between oceanic crust and continental crust. The continental crust is much higher up compared to oceanic crust. This is because oceanic crust is denser. When the pushing oceanic plate collides with another plate, the more dense material will sink. Therefore, if oceanic and continental crust collide, the oceanic plate will sink.
And if the two oceanic plates collide, the more dense plate will sink, right? Nevertheless, how do they differ in more density if they are made from the same material?
Over time, sediment builds up on the slabs due to deposition. The more time that passes, the more sediment that builds up. Keep in mind that sediment is rock broken into little pieces.
And the sediments add for density. So what happens with the denser plate sinks?
The subducting plate dips down below the other plate, creating a trench between the plates. An example of a trench is the Mariana Trench.
That's the deepest trench in the world. It's very famous and unexplored.
Anyways, the plate that subducts goes deeper down into the asthenosphere, which is very hot, and the plate melts back into magma it was created from.
What about slab pull?
Slab pull is the force of the subducting plate on following ocean slabs of ocean floor. The force pulls the ocean floor in the direction of the subducting plate, which means the mid-ocean ridge is pulled farther apart. The subducting plate can also disturb convection currents in the mantle.
How do scientists know how old each slab is?
Well, every so many years, the North and South Pole change, and since electrons point towards the north, they switch directions too, making the visible lines in the slabs. These are called magnetic reversals.
And the farther away from the ridge, the older the slab is?
Exactly. It is also very important to understand that seafloor spreading happens symmetrically, meaning it is the same exact thing on both sides of the ridge.
So new seafloor is made evenly on both sides?
So, do you understand the subject now?
So convection currents in the mantle cause seafloor spreading, and seafloor spreading causes slab pull?
Yes!
And a convection current happens when more dense material in the mantle pushes less dense material upwards, right? And this magma rises up through mid-ocean ridges and hardens into new seafloor, which pushes old seafloor outwards. This causes the seafloor on the outside to collide with each other and cause subduction.